Okay, good afternoon. Sorry I'm running late. Where we are, I've finished chapter 23, and we're skipping chapters 24 and 25. And basically, the way I feel about this, the way I think about this class, I outlined the very, very first lecture, if you remember back that far at all. The first part of this class is sort of descriptive statistics in some way or another, including correlation and regression. Regression is a little bit sort of data analysis, but you can sort of think of it also as just in terms of descriptive statistics. And then we have this middle section of the class on probability, and then chapters, 17 through 20 sort of provide this kind of transitional period where we're talking about probability, but it's probability as it relates to box models, taking many draws from a box, stuff like that, which we sort of need all all those foundations to talk about confidence intervals in chapters 21 and 23, which is, I guess I sort of categorize as data analysis, kind of pure data analysis. And the rest of the class also will be data analysis. So the data analysis part of the class really is confidence intervals and what are called hypothesis tests. So hypothesis tests is what I'll start doing today, and we'll do that. That's sort of the last major topic for the rest of the class. So the way I like to start talking about hypothesis testing is to do a little example with my big cards. And I've separated out 5 cards. That made people get quiet. Pull out the cards. So these 5 cards, ace, king, queen, jack, 10 of spades. And I want to play just sort of this guessing game with these cards. So I have ace, king, queen, jack, and 10 of spades. Suppose I'm going to guess which one will come up next. Okay. And I'm not going to do it 100 times, but imagine that I did it 100 times. So if I did this 100 times, how many would I need to get right? How many guesses would I need to get right? For you to believe I can sort of in general do better than guessing randomly. So my claim is that I can do better than random guessing. Okay. So if you want, I could claim that I'm psychic. I can claim that on some level I have some feeling about the cards, some connection with the cards, that I shuffle them, and then I guess that this one is going to be the jack of spades. And I got it right. Cool. And then I guess that then this one is going to be the king of spades. Cool. All right. Okay. So then I shuffle some more. And I think this one's the pressure. This one, I think, is the queen of spades. And I got it right. So, right. So at some point, you believe maybe that something is going on. Okay. So then if I guess this one's the ace of spades, I got it wrong. Right. So you believe maybe that I'm cheating at some point. If I get them all right, like say I think this one's the jack of spades, and I get it right. So at some point, you believe that something's going on. It may be difficult for you to believe that I'm psychic. You maybe believe that that something else is going on, that, I don't know, I'm not really shuffling them, that I know what order they're in, I know what's going to come up next, the cards are marked, something's going on, right? So the question is, at some point, like people started being impressed maybe once I got about 3 in a row right? Well, what about out of 100? You wouldn't, I mean, maybe you require that I get them all right for you to believe that I can do better than random guessing. This is, like many parts of this class, I try to introduce concepts sometimes by telling you not to think about it. Just sort of, if you watched me do it, like you just watched me do it, and you had this feeling once I got maybe 3 right or something in a row that maybe something's weird or you're surprised or something. So I'm just sort of asking here, if you actually watched me do it 100 times, it would be a little bit boring maybe, but at the end of the 100 times, I don't know, kind of just emotionally, what's your feeling? Like, how many would I have to get right for you to be sort of surprised, or to really think that I'm not guessing at random? So I'm going to throw out some numbers. Anyone want to? 30? 100? So some people are harder to convince. 99. 0. I'll write it down. Anyone else? Any other thoughts? 40? 66? Someone else say 60? 60? Okay. Okay, that's probably enough to work with. So the way we think about this, so I think I wanted you to think about it just, sort of intuitively, roughly. I think as a statistician, the way I kind of try to think about this is, well, first of all, if you did watch me guess, and I am just guessing at random, how many would you expect me to get right? 20, right? If I'm guessing at random, there are 5 choices. Out of 100 guesses, you would expect I get roughly 1/5 of the guesses right, which is 20. And then you might start thinking about the standard error, possibly. And you might think that once I get like a couple of SEs away from what I'd expect, maybe 3 SEs, something like that. I don't know, just kind of roughly. If I get several SEs away from what I'd expect, that's sort of unusual at least, right? So that's something that would sort of make you wonder what's going on. If I got maybe 1 SE above what I'd expect, then you might think, oh, maybe I'm just got a little bit lucky. I don't really have any like psychic ability. Nothing special is going on. I'm not cheating necessarily, but just random. Okay. So essentially, as a statistician, what I think you should try to think about with a question like this is, can the result be explained by chance? Like, is it reasonable to sort of think, oh, that's just random variation, or do you need another explanation? Okay. So when you think about what number to choose or whatever, think about maybe rephrasing this question as this. Can the result be explained by chance variation, or just by chance, or is another explanation necessary? And maybe there's a little bit of gray area, right? Maybe there's a little bit of gray area where if I get like maybe, I don't know, 2 SEs above what I'd expect, you might think, well, that's unusual, but it's not sort of crazy. It's not so unusual that it's sort of outside of the realm of chance, okay? If I got 100 right, it would be kind of ridiculous for someone to watch me get it right 100 times and then just say, oh, I think you're just lucky. You're just guessing at random, but you just got lucky, okay? It's so astronomically unlikely that I would randomly get that right. That certainly 100 you should think can't be explained by chance. There must be some other explanation. 99, I think still, so ridiculously far away from what I'd expect that just intuitively you should reject the idea that that's just random, okay? So these other ones, maybe we need to think about a little bit harder, right? They're more than 20, but it's unclear, maybe just by looking at them, if it would be reasonable to explain them by chance, okay? I'm not sure about this one. So I'm not sure if 0 is just being silly, or if it's saying, well, that is a highly unusual result, and I must be doing something weird if I get 0 right. Or it might be that you just trust everything that I say and you don't care how many I guess right. If I claim that I can do better than guessing right, you just believe me, right? I don't know. So anyway, yeah, so that's one of those explanations, I think. Okay, so let's think about this a little bit more formally. What I'm going to do is, first of all, think about this as a box model. So if I'm guessing randomly, what would my box model look like for counting the number of correct guesses? You want to say what the box should look like? Yeah. 4 zeros and a 1, good. So the 1s represent the correct guess, a 1 out of 5 chance of guessing it right if I'm just, guessing at random. And I'm making 100 guesses. Okay, so the average of that box is 1/5. The SD of that box is, using the shortcut back from chapter 17, big minus small times the square root of fraction of big, so fraction of 1s, fraction of 0s. That comes out to be 0.4. And as we said, sort of obvious, I think, pretty obvious. Expected value is the number of draws times 1/5. That's 20. So that, makes sense, I think. And the SE for the sum of draws is square root of 100. So this is for counting the number of correct guesses. Square root of the number of draws times the SD of the box comes out to be 4. All right, so if you do a little math, maybe then this changes your thoughts about these numbers. 60 is 10 standard errors away from what I'd expect. That's like way off the normal table. That's extremely unlikely due to chance. In theory, it could happen. It could happen that I get 60 right out of 100 guesses, but it's incredibly unlikely to be 10 standard errors away from what you'd expect. This one's even farther. This one, I guess, is 5 standard errors away, right? 5 standard errors away, and that's just a little bit off the table. Also extremely unlikely. This one is, it's 2.5 SEs away from what I'd expect. That maybe is in a little bit of a gray area where it's not kind of extraordinarily unlikely, but it's certainly a lot more than what I'd expect. Getting 2.5 SEs above what I expect would be sort of pretty unusual. Okay, so part of what I'm trying to instill in you from talking about it this way is that it is actually a little bit subjective at what point you would decide that it's not just random, okay? And really, some people might be more easily convinced than others by something like this. Someone who, I don't know, is very skeptical and thinks that, like someone said, cheater, once I started getting a couple right, it might be very easy for you to believe that there's some other explanation, right? Someone else who totally trusts me and doesn't believe in psychics at all might be harder to convince, right? If I say, well, I'm just shuffling these cards. There's nothing special about the cards. I'm really shuffling them, and I say, there's this. If my claim is that I'm psychic and you don't believe in psychics at all, then maybe you require me to get 5 standard errors away from the expected value to really be convinced. You require something very extraordinary to be convinced. Whereas if you're just think, oh, he just set it up, then maybe you believe pretty quickly that I'm cheating or something. Okay. All right. So I just want to sort of give you the idea that this is a little bit subjective. I will give you rules that are commonly used about how to sort of decide this sort of thing, but it is a little bit subjective, and you can kind of see, like, the more I get right, the more you would be convinced, right? If I get them all right, everyone's going to be convinced, I think, that I'm doing something different than guessing randomly, right? And I certainly must be doing something different. But if I get, like I say, if I get 30 right, maybe you wouldn't be so. Maybe some people wouldn't be convinced, and maybe even if maybe those people that would be convinced are still a little bit like not sure, right? So how strong your conclusion is depends on how far away you get from your expected value, and to say it in a more statistical way. Okay, so any questions, thoughts? Yeah?
Usual if you got 20, the first 20 you got right, and then the rest of them, like it still fits into like the usual here.
Yeah. Right. So he said, would you think that it's unusual if I got the first 20 right and then got all the rest of them wrong? So I got the expected value, but I saw something happen that's not not what you expect. It doesn't look random. Okay. So there are lots and lots of hypothesis tests to sort of test for all different things in the world. The one we're going to do now, and we're going to do a few different kinds, but the one we're going to do now is simply to test whether or not, in general, I get too many right, basically. Okay, so it's not sensitive to that kind of a pattern. Although, like I said, there are different kinds of hypothesis tests you can do, which will check to see if there's something weird going on in some other way. Okay, good. Any other questions? Okay, so I'm going to write down instructions of how to do a hypothesis test. And as I do it, I'll kind of talk back to this example. And then once I write out the instructions, I'll go through this example in detail. Okay? This is probably the most complicated thing we do in here. And so the instructions are sort of long. Like the regression method or something like that, the instructions are fairly short. So I could get to an example fairly fast. Some of this may not really make total sense until I do the example. Okay. So, hypothesis testing. What I'm going to do now is what's called a one-sample z-test. So as I mentioned, there are different kinds of hypothesis tests. A one-sample z-test means one sample, basically it's like I have one sets of draws from the box, okay? So the 100 guesses represent one sample. The z just means that I can use the normal table at some point. Okay. So the steps are, first of all, to essentially try to refine this sort of an idea. Can the result be explained by chance, or is another explanation necessary? What those two things are called, these sort of two competing hypotheses, one is called the null hypothesis. What does null mean? Just as an English word. You want to say what null means, roughly? Yeah. So null and void is a sort of common phrasing that those words are sort of used together. Yeah. So yeah. Zero, nothing. Yeah. So all those things sort of mean a little bit of the same thing, right? Zero, nothing, void. In the context of this, a hypothesis test, it means that nothing is going on except for chance. Okay? So there's no other explanation necessary. I'm not psychic, I'm not cheating, nothing's going on. Okay? So I'll say it roughly like this to say that the result can be explained by chance. And the way, so like for the final, I'd like you to include a bunch of different steps, and I'll lay it out in outline form, and once you see a few examples, you'll hopefully get used to it. so the first part of this is, I'll call a chance statement. And it's something like results can be explained by chance. I don't care exactly how you word it. I will try to word it in lots of different ways because I don't want you to sort of memorize something and then just repeat it. I'd like you to sort of understand what this means. It means that, like I said, there's sort of no other explanation necessary. Chance is a reasonable explanation for what we observe. So, if I got like 21 right, you'd sort of say, well, sure, you got a little bit better than what you'd expect, but I don't really believe that it's because of any psychic ability or anything. I just think you got a little bit lucky. It's just random. Okay, so that's essentially what this is saying, part A. Part B is saying something particular to the problem. Okay, so for this problem that I'm talking about, say something like just guessing at random. Okay? All right, so I'd like you to have those two elements whenever you write down a null hypothesis. So hypothesis is sort of one possible explanation or belief, and the other possible thing that we're trying to decide between are these sort of two competing ideas. Can this be explained by chance? Can the results be explained by chance? That's the null hypothesis. Or is another explanation necessary? The other explanation is called an alternative hypothesis. So again, I'd like you to make some kind of a chance statement, which is sort of say something about chance. And the flavor of it should be something like results can't be explained by chance. Second part is, again, something particular to the problem. And so the something particular to the problem, if it's not chance, well, in reality, you can't really necessarily tell what it is. If I just go ahead and guess and I get them all right, you can't really tell why. Okay? So in this particular example, it could be that I'm psychic. It could be that I'm cheating in some way. There are some different possible explanations. But like I said, you can't really conclude exactly why, but you can say that I'm able to do better than guessing at random. So that's essentially what these two things are doing. Is the alternative is my claim. My claim is that I can do better than random guessing. The null is that there's sort of nothing going on. I'm not able to do better than random guessing. Okay, so I want to just mention about those two hypotheses that the null hypothesis should give you enough information to make a box model somehow. So null should and this is I'm just going to say parenthetically for a one sample z-test. We'll do other kinds of hypothesis tests, and this is not quite true, that you would necessarily be able to make a box model based on what the null says. But for this case, you can, for the one sample z-test. Actually, you know what? Let me change that. Let me say it this way. Should help. Yeah, sorry, I want to be a little bit more vague because there's some kind of weird examples. Should help to make Bach-Bus model. Okay, so in this case, the null hypothesis for this, just guessing at random, is enough for you to figure out that the box looks like that, right? Okay, so that's that bit. And okay, so that's step one. Step two, that gives you sort of your two competing hypotheses, okay? So there's no math yet, just kind of a statement of what we're trying to decide between. All right, any questions? Okay, so step three is to mostly do the math, and it's to get what's called a test statistic. And in this context, it's a z-value, okay? So that's what makes it a z-test, is that the test statistic we're looking at is a z-value. So you're sort of used to thinking about z as, in the context of, you know, random stuff like this, box models, is some observed value minus expected value divided by the standard error, right? So our null hypothesis should give us enough information to, or at least help us to make a box model. There may be some things that are not specified. I'll talk about that either the end of today or next Tuesday. But at least the null hypothesis will always give us what we want to compare to, right? It'll always at least give us enough information to get an expected value. So the observed is from our data. We compared that to the expected value. And the standard error is a little bit trickier. Basically, I'll just tell you why it's tricky. Sometimes you need to use the bootstrap method, and sometimes you don't. So, but that issue I'll get into, like I say, either end of today or on Tuesday. OK, so once you get your z-value, then you get what's called a p-value. So in general, the z-value could be either above or below the expected value, but I'll draw this picture as though it's above. This is expected value from the null. Right? The null should give us enough information to get the expected value. And then out here somewhere we have the observed value. That's whatever we get from our data. And if we convert that into standard units, this is EV from null. And then in standard units, or as a z, well, I'll say in standard units, 0 is here, z is here. OK? So we do this calculation, gives us this z, and then this area is p. So the p-value, let's see. I guess I'll squeeze it in here. P-value. I don't have enough room. I need to use another board. So the p-value is a chance. It's the chance of getting data like we got or more extreme given that the null hypothesis is true. OK, so what's the logic of this? The logic of this is that we're going to do some calculations assuming the null hypothesis is true, just like I did up here. I found the expected value in the standard error, assuming that I'm just guessing at random. And then I sort of said, OK, well, you know, if I got 40 right, that's 5 standard errors away. So we just go through this logic of, and that would be a z-value, right? 40 minus 20 divided by the standard error of 4 gives us 5 as a z-value. So then the p-value is very small. So we're doing these calculations under the assumption the null hypothesis is true. And then we look at this p-value, and basically the p-value gives us some idea as to whether or not this could be reasonably explained by chance. If the p-value is very, very, very small, that makes us think that this can't really be just chance, which makes us think that this assumption that the null hypothesis is true must be false. Right? If we end up getting something, the null hypothesis says, oh, there's just chance going on. There's nothing else going on. And then we get something really far away from what we expected to get, according to the null hypothesis. The z-value is big. That means the p-value is small. The p-value, again, is the chance of getting data like we got or something more extreme. So if this z is like 5 standard errors, then this p-value is going to be very, very small, very close to 0. And that's basically saying, well, if the null hypothesis is true, you pretty much never get something like that. But you did get something like that. So that makes you think the null hypothesis must not be true. Okay? So that's the logic of the process we're going through, is to assume the null hypothesis is true, do all our calculations assuming that it's true, and then at the end, kind of look at this result and think, well, is this really plausible? Could we really have gotten data like this if the null hypothesis is true? And if it's not really reasonable to randomly have gotten data like this, then we must reject our original assumption. Okay? So actually, let me say one more thing. So p-value, the smaller the p-value, I'm just going to say it kind of as a general statement here. The smaller the p-value, the stronger the evidence against the null hypothesis. Okay. So last step. Last step is the conclusion. And I'm not going to, I want to get to an example, so I'm not going to talk about this in a lot of detail. I'll just list the 3 things I think you should have in here. So statistical jargon. And I'll tell you what I mean by this after I do the example. There's sort of like particular words that statisticians use, like 95% confidence is a bit of statistical jargon that means a particular thing. So there's some words that I'll tell you to use as part of your conclusion. And then part B is a chance statement that it sort of roughly reflects either this chance statement or the alternative. If through our z-value, p-value, we decide that we think the null hypothesis is reasonable, then this chance statement will roughly look like the chance statement over there. And there's some things that I would say maybe a little bit differently. I'll describe that when I do an example. But roughly, this is going to reflect either if we decide the null hypothesis is reasonable, it's going to say something like, the results can be explained by chance. If we decide that if this is so crazy that we don't think that it could be explained by chance, then this will roughly say that can't be explained by chance. And the last part is something particular to the problem. And again, this will roughly correspond to what whichever hypothesis we decide that we like. Okay, so like I said, a little bit of statistical jargon, which I'll explain later, and then these 2 parts roughly reflect whichever hypothesis we've decided that we believe. Okay, so I realize it's sort of, it's a lot of steps to talk about without doing an example. But does anyone have any questions? Anything come up for you now before you see an example? Okay, so let's do this example in detail. Actually, maybe I'm just just going to write down the problem here because I don't want to really erase anything else yet. So suppose I do it 100 times and I get 30 right. Actually, these examples take kind of a long time, and so if I don't take a break now, I think it'll be sort of late before I take a break. So I'm going to take a break, OK? I'll take a little break, and then I'll do an example. OK, why don't we get started again? I don't want to ever lie to you. So the cards are marked, just so you know. I don't want to deceive you. Okay. So suppose I get 30 right. So that's my data. That's my observed value. So I'll go through the math. Well, I'll go through the null and the alternative first. And I wrote it out here already, right? What the null is. So I will just use this. OK, so the null hypothesis is, the chance statement is, like I said, something like the results can be explained by chance. And something particular to the problem, I'll just say, is that I'm just guessing at random. OK? So that's again, the null hypothesis is sort of saying that there's nothing going on other than just random chance variation. And so that's trying to just hypothesize that, well, 30 is something that could happen just randomly. Okay? It's reasonably close to the expected value, and it just can be explained by just random guessing. OK, so that's that. The alternative, I'll just use this also. Oops. So alternative says that roughly the results can't be explained by chance. OK, so it's a chance statement. Results can't be explained by chance. So again, that's sort of saying that I can do better than guessing at random. That's what it's sort of saying specific to the problem. So this is what you would tend to believe if I get so far away from the expected value that it sort of doesn't make sense. It's not believable that chance is a reasonable explanation. OK, and then I said null should help make a box model. And the way the null helps you then is that you just sort of look at it and you think, well, OK, if you're just guessing at random, what does that mean? If I'm just guessing at random, I should have a 1 out of 5 chance of getting it right. I'm making 100 guesses. I can get my expected value. I can get my standard error. OK? So now, basically, with all this done, I'm ready to get my z value. OK? So z value is a test statistic. And it's observed minus expected divided by the standard error. And there's a slight little wrinkle for this problem, which comes up sometimes. It doesn't come up very often. But I'm thinking of this as being observed minus expected divided by the standard error. But let's think about what the p-value really means. In the end, we're going to use the z-value to make a p-value. The p-value is the chance of getting data like we got or more extreme, given that the null hypothesis is true. Okay? So in the context of this problem, I'm using this box model. And I want to find the chance of getting data like I got, 30, or more right. So if I just, as a probability problem, if I said, with this box model, what's the chance of getting 30 or more right? Would you do 30 minus 20 divided by the SE? There's something that you might want to correct for. So what am I hinting at? You want to find the chance of getting 30 or more right. So if you think about what the probability histogram looks like for this, we got 20 in the middle. That's what we expect. There's a bar over that. There's some bars over here. And then at some point, there's a bar over 30. OK? So there's bars, 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 bars here. So there's a bar over 30 here. And I'd like to find the chance of getting 30 or more right. So when you go to do normal approximation, when you go to get your p-value, well, you'd really like to find the area of that bar and everything to the right. If you think about literally what the p-value says, the probability of getting, or the chance of getting, data like we got, 30 or more. Okay? So I'd really like to use the left edge in calculating my z. Okay? So generally, this is the way to think about it. But you have in mind that it is a probability in the end when we get the p-value. It's a probability calculation. So anything we've learned in chapters 17 through 20 or whatever applies. So in particular, since this is a discrete probability histogram, consecutive numbers in the box, right, the zeros and the ones, and we specifically want to find the chance of 30 or more, then we should use 29.5. So when I calculate z, I'm going to get 29.5 minus the expected value of 20 divided by the standard error of 4. And that, where am I here? That comes out to be 2.4. Okay? So that's my z, 2.4. So then when I come to step 4 to get the p-value, I just need to look that up on the normal table. Here's 2.4. And look that up on the normal table. I get an area in the middle of 98.36. So this in the middle is 98.36. And the p-value, this area is 100 minus that divided by 2, which comes out to be 0.82%. Okay, so that's my p-value. Okay, so that's pretty unlikely, right? It's a little bit less than 1%. If you watched me do this and I got 30 right, I think you ought to be at least a little bit surprised. However, it's not crazy. It's like, a little bit less than 1%, but that could happen just randomly. So, I mean, you wouldn't necessarily, you wouldn't necessarily be totally convinced that something's going on. But like I say, I think you should be at least a little bit surprised. Now, in part 5, the conclusion, I'm going to answer this question. I'll write in what I would write for each of these parts, and then I'll go back and kind of say more generally what your kind of guidelines are for making your conclusion. Because like I said, it is a little bit arbitrary. So before I erase it, I'll just remind you again, I think this is important. This is important for really seeing the logic of the hypothesis test, that the p-value is the chance of getting data like we got, or more extreme, given that the null is true. So like I said, we did all these calculations assuming the null is true, got our expected value, our standard error, got our z-value, and then the p-value is the chance of data like we got, 30 or more extreme, given that the null is true. Okay, then this bit here, the smaller the p-value, the stronger the evidence against the null. So if I had gotten, 40 right or something like that, 40 right, I'm out here somewhere, the z is way more, and the p-value is way less. So that would be very strong evidence against the null if I managed to get 40 right out of 100 guesses. This is maybe a little bit of a sort of gray area. That's why I chose it. Okay? Okay, so that's this bit. Now, to do the conclusion, so the A part is the statistical jargon, and I'll give you the jargon thing that I'll say about this. And after I do the example, I'll say more generally what you should do in every situation. So we say here this kind of statement, reject the null hypothesis is like a very common phrasing in hypothesis test, which is essentially saying that you don't believe the null hypothesis is true. Okay? The 1% level means that the p-value is less than 1%. Okay? So that's basically all that's saying, is that this is kind of our conclusion, that we should reject the null. We don't believe that this is just because of chance, and this is kind of how strongly we feel about that conclusion. Okay? And like I said, I'll give you more general guidelines in a bit. Now, I would not quite say it can't be explained by chance. So when we say we're rejecting the null, we favor the alternative. The alternative says the chance state, right, I'm kind of going through this outline. A is statistical jargon, B is a chance statement. And I said before, it roughly should reflect the chance statement here, that the results can't be explained by chance. I'm not quite comfortable saying that the results can't be explained by chance, because they could have been chance. I haven't really proved absolutely without a doubt that it's not just random, okay? This is pretty strong evidence against the null hypothesis, is the way I would think about it. So I'll say it doesn't look like chance. But I don't want to directly copy what the alternative says, because I haven't proved that the alternative is true. What you have here with these hypothesis tests is you don't have these strong black and white conclusions. You sort of have evidence in favor of one thing or another, but you don't know absolutely for sure for these kind of in-between results. Like 2, maybe 3 standard errors away from what you'd expect is pretty unlikely, but it's not like off the chart, crazy, unbelievable, right? Okay. So it doesn't look like chance. And then about the problem, I would say something like it looks like I can do better than random guessing. Okay. Just to bring it back to, okay, what's the actual question? What am I wondering about? And the original question was basically, can I do better than random guessing or not? Right? Okay, so any questions about this? Like I said, I'll say things more generally, like what you would say when, depending on the p-value. But yeah, question? Or no. So what you do really is you should decide ahead of time. Okay, so there's a little bit of a philosophical issue here, which I'll say briefly, and then I'll say what we'll do for this class. The philosophical issue is that it's sort of cheating. We're in conducting this experiment, this series of 100 guesses. I asked you at the very beginning, what number would convince you? Okay, it's sort of cheating to watch me do it and then decide whether or not my results are convincing. Really, you should decide ahead of time what would convince you. Like if someone came in here and claimed to be psychic and got some results, I feel like to make it kind of a reputable experiment, you should decide what the person has to do, what standard at which you're going to say, okay, you proved it, you're psychic. You should decide what that standard is going to be before you do the experiment, right? If the person does the experiment and then gets 30 right or whatever, and then you decide, oh yeah, well that was good enough, then it seems a little bit fishy. So really, you should decide what your cutoff lines are going to be ahead of time, okay? And I'm a little bit cheating by getting my results, finding 0.82%, and then say, oh, look, I got something less than 1%, okay? Now, there are basically 2 cutoff lines that people use in real life, which is 5% and 1%, okay? And they're just arbitrary. They're just nice round numbers. Now, for the purposes of this class, I'll do the following. So for the statistical jargon part, actually, let me write a little bit about, and then I'll come back to this idea. So guidelines for conclusion. And basically, we'll divide this into 4 different categories. The first one is when the p-value is bigger than 5%. The A part of the conclusion, the statistical jargon part, is that we can't reject the null. Okay, so it's sort of a double negative. And the reason for the double negative is that you haven't proved that it's just random. So like suppose I got 22 right. or maybe 24 right. 24 right would be one standard error more than what you'd expect. So, you know, it's better than what you'd expect, but the p-value there is going to be, well, one standard error above would be about, you know, ignoring the continuity correction just for a second, roughly 68% in the middle, tail p-value would be 16%. So it's more than 5%. One standard error above what you expect could be explained by chance. It could be that I'm able to do better than guessing at random just a little bit. Or it might be that I'm just guessing at random. And you can't really tell which, right? You can't really say if I got one standard error above what you'd expect, you can't say for sure that I'm just guessing at random. Okay? So I'm not quite comfortable saying like the null hypothesis is true here. Can't reject null is basically saying that I don't have enough evidence to be convinced that I'm not just guessing at random. Could be guessing at random. Maybe, you know, maybe I may have like a slight psychic ability or something. But I can't, this is basically the, you know, the way I'd like you to say it is they can't reject the null. Some people will say here, accept the null. And I don't care if you write that as long as you understand this idea, okay? When you say accept the null, I think the way you should think about it is that sort of the null hypothesis is an acceptable explanation. It could be true. It's not that you've proved that it's true, okay? So you haven't like proved beyond a doubt that it's just guessing at random. All you're saying is that you don't have sufficient evidence to reject it. So that's why I sort of prefer this wording, even though it's kind of a double negative. Okay, questions about that part? Okay. So the chance statement about this. So, you know, up there I have statistical jargon, chance statement. The chance statement part, I'm fine with just writing this. The results can be explained by chance. That statement there does not say that it is chance. Okay, I don't want you to write here it is chance or something like that. That's all right. Can be explained by chance. I'll just say a different way maybe. Could be just chance. Anything like that is fine. Okay. Like I said, I don't really care if you use the specific words I use. It's more important to me that you understand the idea behind it and not just, you know, don't just memorize and write it down. Okay? So I can't give you a guideline for part C because it depends on the problem. For this one, it looks like I can do better than random guessing. So something like this where it's sort of like it's saying some statement about the actual problem. Okay? All right, questions on this? Okay, so that's the first category. Everything else is going to reject the null hypothesis at some level. So if you get a p-value that's between 1 and 5, okay, so if you get exactly 5, I'll include it in this category. Exactly 1, I'll put it in the next category, which is a little bit silly because looking at your normal table, there's no way you would get a p-value of exactly 5. Okay, there's always like, you know, some decimal p-value. Okay, so this I will say reject null at 5% level. Another way that this is sometimes worded is that it's statistically significant. So that means significant. So the hypothesis test is sometimes called a test of significance. It's trying to determine whether or not the difference between the observed value and the expected value is significant. Now, significant has this very specific statistical meaning, which is literally that the p-value is less than 5%. If I say statistically significant, or if I just say significant, that literally just means p-value is less than 5%. Okay, it's a specific meaning to a statistician. Okay, so then the B part is that, this is not that small of a p-value, right? If I had gone through this calculation, I got a p-value of like 4%, what that's saying is that if the null hypothesis is true, if I'm just guessing at random, about 4% of the time, I would expect to get data like this or something more extreme. Which, 4%, it's kind of unlikely. It's unlikely enough for me to think that I don't think the null hypothesis is true. I don't think it's just chance. But really, it could be. It's not super strong evidence. So I'll just say something like doesn't look like chance. Because you notice here, I think the data sort of favors the alternative instead of the null, but I'm not going to quite say anything this strong. I'm not going to say the results can't be explained by chance. P-value 5% or like 4% maybe. It doesn't look like chance, but it could have been chance. It could be that the null hypothesis is true and I just got lucky. Okay, so questions about either of these? Okay, so the next one, I have not, so here I got a p-value. Let me just rewrite it. So the next one is this actual category that I got, where the p-value is less than 1%. So here I'm going to say reject null at 1% level. You could say doesn't look like chance. If you want to, both. These are a little bit interchangeable in terms of the words you use. You have a slightly stronger statement here. I'll say it this way. Okay. You could say the same thing as I said before. I'm just going to word it in a slightly different way just to give you a different feel for it. Chance is not a good explanation. Chance does not really seem like a reasonable explanation for this result. It's less than 1%. It's unlikely enough that I'm really starting to feel like I don't believe the null hypothesis. This is pretty strong evidence against the null. All right? And let me just write that down the last one. The last one is when p is essentially 0. This is when z is off the table. Okay? Now, the table I think goes to 4.45 as a z-value. If you got more than 4, maybe, this is a little bit arbitrary. Okay? So, if you got a little bit around 4 standard errors away from what you'd expect, I would accept either answer. Really, it's just, as you get a bigger and bigger z-value, smaller and smaller p-value, you believe more and more strongly that the null hypothesis is not true. So once you get to where it's really, really tiny, really far away, you can just say reject the null. Okay? You don't believe the null hypothesis is true. It's not due to chance. So that's once you get so far away that it's just unbelievable, then I think it's okay to just say, yeah, the null hypothesis is not true. This is just not due to chance. Okay? All right, so let me go back up a little bit and just, I was saying sort of philosophically, you should choose your cutoff level, your line you're going to draw, before you do a hypothesis test. For this class, we'll always choose 5% as our cutoff line. And strictly speaking, I shouldn't do this then. I shouldn't give you a different category here. I should just say either the p-value is less than 5% or it's not. That's my arbitrary cutoff line. However, I'm going to include this because sometimes in real life, you'll see this. You'll see reject null at 1% level. And like I say, what that means is that the p-value is less than 1%. So I do want to expose you to this, this other cutoff line that some people will use. And essentially, this is just a little bit stricter. This is just saying, okay, I'm a little bit harder to convince. I require a p-value less than 1% before I'm going to reject the null and believe that it's not due to chance, okay? So yeah, so for this class, you can do it this way. Some statisticians might complain that I'm sort of allowing you to look at your p-value and then decide if you're doing 1% or 3%, or sorry, 1% or 5%. But like I say, I feel like this is a reasonable way to approach it. Okay, questions about any of these categories or conclusions, anything? Okay, so just in terms of the part C, something particular to the problem, I think I've said it for most of these, but if I did this card guessing game and I got a p-value bigger than 5%, I'd basically say something like, looks like just random guessing, or it could be just random guessing, something like that. For the second category, between 1 and 5, I'd say something something like this. It looks like I can do better than random guessing, or it seems like I can do better than random guessing. Some kind of slightly wishy-washy statement. It doesn't look like it's chance. It looks like I'm doing better than random guessing, but we can't be absolutely certain that I'm not just a little bit lucky. Okay, and then this category, I would be pretty firm. I would say, I'm able to do better than random guessing if I manage to get something off the table. All right, questions, thoughts? Okay, so I realize this lecture, there's a lot in it, okay? Once we get all these steps down, this is basically what we're doing on some level for the rest of the class. So it'll, I think, seem easier and easier. So let me do one more example. I think I'm going to, the examples in this chapter tend to be kind of long, so I think I'm not going to have a chance to talk about this one in total depth, but I'll do the math at least. It's kind of an old favorite example of mine. It has Botox in it. Okay, so let's think a little bit, first of all, about what the plausible story here is. So first, let's talk a little bit about Botox and about stroke recovery. So what is Botox? Anyone tell me what Botox is? Yeah. It's it's made from botulism. Anyone want to say what botulism is or what Botox is for? Sorry? Yeah, so it paralyzes your muscles. So botulism is I guess a bacteria. It's an anaerobic bacteria, meaning that it can live without oxygen. And it's very rare. The most common way for people to get it is if canned food has been improperly sterilized. And the way that you can avoid it is if you ever have either commercially canned food, or maybe if someone cans tomatoes or peaches or whatever and gives them to you, if it's ever bulging, it should be when in the proper canning procedure for home canning, what happens is that you can it while it's hot, and then when it cools down, the top gets sort of sucked in, so it's nice and tightly sealed. If it's instead pushed out, that's an indication that something's growing inside, okay? So don't eat it. For canned food also, if you ever see a commercially canned, this would be very unusual. But if you ever saw really old canned food that is swollen somehow, the can's bulging a little bit, don't eat it, okay? There's something growing in there. So like I say, it's very rare. Don't worry about it. Don't lie awake at night. The toxin in it is I think it's called botulin. I think that's what it's pronounced. And maybe there's another syllable in there. Anyway, the toxin it does paralyze you. So essentially, if you get this bacteria inside you, it'll paralyze your muscles wherever it grows to. So if it grows to your heart, you just die, right? So it's, it's dangerous if you get it, but like I say, it's very rare. The way that this is used pharmaceutically is, as I think most of you know, by real housewives all over the world, to inject into your face, mostly. So if you do it when it's dead, it's not going to spread, it's not going to kill you, but it will slightly paralyze your muscles wherever you happen to inject it, which is like, why Joan Rivers can't feel her face and she can't smile and things like that. It basically smooths out your wrinkles. You're unable to like furrow your brow or get all upset and wrinkly. So that's the way it's used for like cosmetically. So maybe that's enough about Botox. Strokes. Well, okay. So anyone want to say anything about strokes? What's a stroke? How do you get a stroke? What happens? Yeah, so common ways that you have blood clots. You have loss of blood flow to part of your brain for some period of time. And so what happens, it can be, you can have very serious strokes, you can have relatively mild strokes. Loss of oxygen to your brain may mean that part of your brain just dies, okay? And the effect that the stroke has on you can vary widely depending on what part of your brain has a problem, okay? So if it has to do with your language centers in your brain, sometimes people will lose the ability to speak. Sometimes people will lose motor control of some parts of their bodies. As I say, anything your brain does can get screwed up by a stroke. Okay, your brain is kind of an amazing thing, and a lot of times your other parts of your brain can regain the function of the part that died. So like if you lose your language, like some other part of your brain will learn how to talk, basically, and so learn how to move your arm or something like that. Okay, so often you can recover somewhat from strokes, but it's not perfect, but often you can recover somewhat. Okay, so why are these in any way related? Well, someone working for the company that makes Botox had the idea that one of the things that happens with stroke sometimes is that when you lose loss of one of your limbs or part of your body, what happens sometimes is that rather than being sort of paralyzed and unable to use it, your brain is sort of constantly firing a signal to contract that muscle. So you see sometimes people with strokes will have part of their body that's like kind of like messed up. It's like constantly flexed in one position. Bless you. Some people that work at the company that makes Botox, the Allergan Corporation, had this idea that, well, if it's constantly flexing, if it's constantly clenching like that, maybe if we inject a little Botox in there, that'll kind of neutralize it and paralyze it a little bit so that you can't contract it continuous like that. And maybe you can achieve some kind of a balance there where you regain some use of of that part of your body. And at least, so one problem with that symptom is that if you're constantly clenching part of your body, it's painful. Okay, if you like clench your fist all day, it's going to hurt. So if you then paralyze it a little bit, at least maybe it won't be painful. Maybe ideally, maybe you regain some functionality, but at least their hope was that you would be able to not hurt as much. Okay, so I think I don't really have time to do it. Well, maybe I'll do it just so that you don't wonder over the weekend if it works or not. So I'll tell you what the z-value ends up being. Okay, so next Tuesday I'll flesh out what the null hypothesis should be, what the alternative hypothesis is. I'll just give you the data for now. So they had 63 stroke victims. And I'm not going to describe their problems very specifically. I'll describe it in more detail next Tuesday. But basically, they had some problems with their hands in some way. Pain, inability to use their hands in some way. And they injected Botox into these stroke victims' hands, and 83% showed improvement. Okay? And like I said, I'll be a little bit more specific on Tuesday about what I mean by improvement. So that looks kind of impressive. 83% improve. But then, as I said before, some people just improve. Some other part of their brain takes over the function, or they get better in some other way. So you might be curious, what should we compare that to? Okay? So that's essentially getting at what should the expected value be, right? We observe 83%. What would we expect? So in general, about 53% of similar stroke victims improve. Okay, so that looks pretty impressive. Compare 83% to 53%. These people did a lot better, but it's kind of a small sample size. So you might be curious, what's the standard error, and do some math. And I'll just tell you, I'll do all the calculations on Tuesday, but the z is 83% minus 53%. This is observed, expected. The standard error turns out to be 6.4%. And this gives us a z of 4.7. Okay, so this is off the table, right? So the p-value is essentially 0. So we conclude that this can't be explained by chance, okay? So I'll talk about it in more detail on Tuesday, some issues, problems with this particular study. Bottom line is that actually Botox is used, and it seems to help people, okay? But I'll give you a full story on Tuesday, okay? Have a good weekend. Bye.